Good afternoon, Stefan Reichelstein, and pleased to be here today and give you a perspective from economics and business on a particular energy source, and that is solar PV. It's a topic that I've got a slight bias here in the picture. I'll continue. Hopefully they'll figure this out. So this is a topic I've gotten interested in a couple of years ago, and since then I've sort of been able to get some graduate students here to work with me on this. This particular project is joint work with Mike Yorston, whom we let graduate in the Department of Management Science and Engineering. He was a very trusted and helpful co-author. So when somebody like that then graduates, you're of course happy for the person that they move on, but you're also losing somebody with whom you very much liked working. So in terms of the motivation for this paper, I think Dan set it up almost perfectly for me. You saw the slide, or several of the slides, in which he made sort of passing reference to a comparison really across different energy and electricity generating technologies and how they stack up in terms of cost. And we hear a lot of that. And what motivated us in this was really the question, where do we stand on solar PV and where are we going? The first observation in this is the range of estimates and opinions on this is mind-boggling. There is just no consensus as to where we stand, the world stands for that matter, and then even more complicated, where are we going in the future? So this has sort of motivated us really to dig in there, and there are two explanations for the wide range of estimates we have. One is people use different methodologies when they arrive at these cost calculations, and that turns out to be true. So if you check a little, dig a little deeper, you'll find there is tremendous variation in that. And the second aspect is they use different inputs in terms of technological parameters that bear on this. So that the combination of methodology and different data inputs, so to speak, is ultimately responsible, I think, for this wide range of things. And then hopefully this type of research will make this debate, push this debate forward in the sense that it makes more transparent where really the differences are and what's ultimately responsible for the different forecasts that we have seen. So here is, as an opening slide, something that I think is uncontroversial. Everybody agrees solar PV has been growing very rapidly on a worldwide scale. In particular, we have seen, if you compare the years 2009, 2010, you see roughly a 250% increase from 2009 to 2010. More importantly, if you look at the whole history, the cumulative installations of investments in this area, 2010 basically was as large, with 17 gigawatt, was just about as large as everything that had ever been installed in this industry worldwide before. And this trend seemed to be holding up as we go into 2011 now. In other words, we're once again, in 1 year alone, worldwide installing as much as has ever been brought online in the past. In this whole debate, where does solar stand, where it's going? People point out correctly there are federal tax incentives at work here, and there are also local tax incentives, or at the state level tax incentives, and in different countries, of course, these rules are different. What I want to point out here quickly, and I'm going to come back to that sort of when we peel away the layers of this onion. For the US, there's first of all a 30% investment tax credit for solar installations. There is secondly a very favorable accelerating depreciation schedule at work, which basically means you get tax savings because you get to write off your investment very early. And then finally at the state level, we have things like renewable portfolio standards, which provide another form of subsidy. So that's important in my mind at the end of the day to see how important, how central are these types of subsidies to the overall economics of the situation, and what would happen in the future if they were taken away. In other words, is what we're seeing in this industry largely driven by tax incentives and tax subsidies, or is it technological improvement, or a combination of the two? Okay. There's also no question, and once again, Dan had a slide on this, we have seen over the last couple of years massive entry into this industry of panel manufacturers. Panel prices have come down some 40% in 2011 alone. I think Dan again quoted you that statistic. The big question then is, can we parcel this out? To what extent is this really a result of cutthroat competition that has come about because we have arguably excess capacity in this industry, and to what extent are we seeing technological change and cost improvements driving that drop in prices? Again, all of these factors are there at the same time, and this type of research is supposed to, or is intended to, sort of separate out these factors and shed light on the relative magnitude of the individual components. Okay? So basically, I won't try to go through all my slides, unlike I'm not going to try to produce Dan's cartoon here by going through them that quickly. If I run out of time, you may perhaps in the Q&A part ask me to show you what's on the slides that I didn't show. First question that I want to get to definitely is, if we look at it today and we compare electricity generated from solar PV, how does it compare to fossil fuels? What are we comparing, what technologies and what scale of investment are we looking at? Well, we're going to basically run this sort of horse race in 4 different ways. And once you have sort of the methodology straight, it is really not all that difficult anymore to add to it. So we're going to look at both crystalline silicon and thin film. And we're going to look at sort of at 2 different types of investors, one being essentially an independent power producer, a utility, that builds this thing on a utility scale, so greater than 1 megawatt, or the alternative scenario, which turns out arguably to be sort of the more interesting at the end of the day, is a commercial scale installation. So think of a retailer with a large rooftop. Think of a Stanford University that has ample rooftop in a favorable location and can just add panels there. Okay. If we get answers to question 1, the next one immediately is, well, there are, of course, a lot of factors that are shaping ultimately this question of how cost competitive are things. Which ones are the most crucial ones? So we have things like location, we have tax factors, we have panel prices. We want to sort of basically do a sensitivity analysis and try from there to say which ones ultimately have the greatest impact, in particular as we look to the future. And the third question is one that I think sort of speaks a lot to the policy debates that we have been hearing about. Some people, you will find people who will say, well, once the subsidies go away, solar is really in a pretty hopeless condition unless there is a technological breakthrough. Earlier in the week, you heard about work that has the potential, work that's being done here that has the potential to really lead to such breakthroughs, disruptive technological change. The question that we're posing here is, since that's so hard to anticipate, let's just stick with what we have and assume that the continual and or continuous change and improvements that this industry has experienced over the last 30 years, if that were to continue, where would that leave us in, say, 10 years or so? Would that be enough? In other words, do you really need the breakthrough innovation, or would it be good enough to just keep going with small incremental improvements the way we have in the past? Okay, what's the metric in all of this? Well, Dan, on one of his slides, had on the y-axis, he had a measure that's called the levelized cost of electricity. That is sort of what's being used in the industry, and we're using that too. So what you're basically trying to do there is you're trying to look at very different technologies in terms of the original investment that's required, the useful life of the facility, your ongoing operating costs, your taxes. You're bringing all of that together into the equation. Unfortunately, and here's sort of a warning, when you sort of look a little more carefully, you'll find the implementation of this concept, even though everybody uses the word levelized cost, is far from uniform. There's a lot of slippage there, and I think that's responsible for the diversity of estimates that we're seeing out there. I think I don't want to go too far sort of into really the technical aspects of this. A very good verbal definition you see here on the screen comes from the MIT cold study from 2007. It basically says, think of this as this levelized cost as a break-even price. This is what you would on average over the whole life cycle of this plant, what you would have to sell your electricity for, so that all the parties that are stakeholders in this, your equity investors, your bondholders, the government, your employees, of course, they all get paid off, so to speak, in a competitive environment, if you want to think of it this way. So that's ultimately what we're solving for in this. For those of you who sort of have an economics bent, I'm trying to argue independently. Think of this as what economists sometimes refer to as a long-run marginal cost, as in this levelized cost calculation. Okay. So if you do a little bit of work, you can break this levelized cost into three components. The first one is what you may call the unit variable operating cost. That turns out to be totally inconsequential for solar, but is a huge component for natural gas. Basically, it's your raw material that goes into the production process. Then you have fixed operating costs, again, relatively minor for solar, also not that big for gas, but much larger for coal. And then comes the last part, and this is really where the whole action is when it comes to solar, and that is your cost of capacity. That's basically the initial installation that you have to put in to generate the kilowatt hours in the future. Okay? And the final thing that can be built in there, this is all, I mean, this looks a lot simpler than it is, but I think for the purpose of this talk, that's also all you need at this point. A tax factor, which basically summarizes, so that gets sort of added as a markup to the cost of capacity, that summarizes the whole effects of the current tax regime that are in place, including the investment tax credit and the depreciation rules. All right. So when you do all of this, you ask yourself, where is this facility and under what conditions are they buying the inputs here? So what we do in this study is really systematically take the perspective. We want realistic values in the sense that they have been observed. We're focusing on at the end of 2011, so it's already a couple of months outdated, if you want to. So the values should be as good as possible in terms of what we see out there, yet at the same time, they should be realistic. So best but realistic scenario is sort of the approach of doing this. So that means in particular in terms of location, we're in a place here in the US, somewhere Southern California, Arizona, somewhere around there. So when you look at the input variables for this, a thing like the so-called capacity factor, that basically tells you the percentage of the electricity that's being generated relative to what is theoretically available. The capacity factor of 20% is very high, and you wouldn't get that in most locations in the US, but you can get it in some very good ones. Okay? Perhaps here also a point to note, the input prices, module prices, and the so-called balanced of systems, that's basically the capacity cost that I talked to earlier here. And we're marking those at around $2 to $3 per peak watt. Now, arguably, those are very favorable values. On the other hand, once again, they have been observed for panel prices were even now in 2012 below $1 per peak watt. The other thing to pay attention to, in a moment I'm going to talk a lot about module prices and their future. Those really have come down a lot. The balance of system costs in the past haven't been talked much about. So that's basically cabling, wiring, and a bunch of other things that are required. They are now as large as the panel costs, but they have been far less dynamic in the past. And I think when you talk to people in the industry, that's going to be sort of an increasing focus in terms of cost improvements going from here on. Okay, so you take your inputs, you have your overall formula to calculate this life cycle cost, and you run that, and here are the results. This is basically the answer to my first question, where are we today? And you see in this 2x2, we have for crystalline silicon and utility scale, we're coming up with about 8 cents per kilowatt hour. So first observation, if we compare this to natural gas, Dan talked about this extensively, there is still quite a delta. For natural gas, the same calculation would bring us to about 6 cents, 5.8 cents per kilowatt hour. However, that's based, Dan alerted us to the question, what's happening to natural gas prices? That's based on an average calculation which takes the price of natural gas. Remember, that's of course the main cost component in generating electricity from natural gas. We're taking there a 10-year average. If you plug in the latest values, that number is going to go down much further. So that would make it harder for solar here. Okay? The two technologies, silicon and thin film, are sort of basically running neck and neck. Like in the major political candidates in this campaign at the moment. That you can't separate them quite clearly yet at this point. And that turns out to be case sort of true in all the scenarios. Perhaps the most important thing that I want to draw your attention to is the combination of silicon and commercial scale. So this is your Macy's or your retailer that puts things on a rooftop. Obviously, they have higher costs than a smaller utility scale project. But the question to ask is, what price do they have to beat? Well, if this is the wholesale price, that's what we looked at for utility, then it doesn't look so good. But if you take the retail prices, it is actually already competitive, in particular with prices that you pay in areas like Southern California, which tends to have high retail prices. So they are already there. Now, as I said, I wasn't going to work through all of these slides. Let me just tell you, in terms of the sensitivity analysis, by far, this shows, I'm not sure you can read this, the different colors here correspond to the impact of different ingredients in the model. And the one thing I want you to take away from this is capacity factor, location. Basically is a huge driver in all of this. What this tells me in one line is a locale like Germany, which in the past has been one of the most aggressive parties in subsidizing solar. They really have a long way to go. Or you can put it more starkly than that. So as I put it here, an almost insurmountable disadvantage for a northern location. Two more thoughts here, and then I'll turn it over to questioning. We have heard a lot about this industry, panel prices coming down because there has been so much entry into this industry. Try to parcel that out and ask yourself, where would that industry have been just given the path that we have seen over the last 20 years for panel prices? That turns out to ratchet up our numbers by about 12 to 15%, so not as dramatic. What is dramatic is if you take away the subsidies, the tax subsidies, the federal tax subsidies. Remember that worked its way in the tax factor in our calculations. So what that would do is almost increase our cost measure by 75%. Then solar in this situation really would not look that good compared to fossil fuels. But the last thought here, here's our learning curve. This is a famous graph which plots cumulative production against module prices that we have observed. And this is on a logarithmic scale, so it's log linear. The thing to ask yourself now, if we just keep plodding along, so to speak, no breakthroughs, the industry just keeps going, where is that going to leave us in a couple of years? And here is the final result. Basically, we project from this model that utility scale PV will be cost competitive with natural gas by 2020, if you still hold on to the subsidies, but then it would really catch up with gas, assuming that the gas prices are not staying as low as they are at the moment. But perhaps more importantly, look at the smaller installations, the commercial scale installations, and assume you take away the federal subsidies in 10 years. If the industry just holds on to the learning pattern it has shown, our projections would tell us that within 10 years, solar would catch up, at least in that dimension, to fossil fuels, even when you take the subsidies away. Okay? So basically, the answer here might be no breakthrough required, but make no mistake, in order for the learning to happen, in order to be able to go down that learning curve, the volume has to be there. But the volume will also only be there if the tax subsidies are in place for at least that time period. But it does provide, in my mind, an answer to the thing, well, do you need indefinite subsidies in order to sustain it? From those numbers, I conclude the answer is no. Okay, with that, I'll turn it over to questions. Yes?
So a big part, as you explained, of evaluating the prospects of solar or a lot of different renewable energies is the methodology that's used to evaluate innovation over a period of time. And it seems like from the literature that endogenous growth theory is kind of doing a decent job of at least explaining innovation. I was wondering if you could elaborate on some of the techniques, and it seems like you were indicating the learning by doing effect, that if we just look at a trend and learning by doing over years, that's one of the ways we model innovation. Could you elaborate on some of the ways that you think are best to look at how innovation occurs over the long run in context of solar?
Okay, so I think the graph that I was glossing over is this one here, which sort of has played a prominent role in this whole literature. This is, first of all, it's at an aggregate level, and it looks at prices over time. And the observation that sort of here for the solar industry has been made at large is that it has really conformed remarkably well to this has a name. It's called the 80% learning curve, or the 80% experience curve. And what it says is every time you double the cumulative output in this industry, your costs, in this case price, the two are not the same, but that's what you're using as a proxy, your price drops by 20%. Okay? There's a lot has been written. So this is basically innovation at the level of the panel manufacturers. Remember, we have two layers here, the panel manufacturers and the facilities that are installing the solar panels. There is a lovely article by Richard Swanson cited in the paper. By the way, the paper, I presume, is available online that I'm basing this on, which sort of argues in detail what are the sources of learning and behind this learning curve from a manufacturing perspective. And I don't have the time to go over that here, but I think that would be sort of a good starting point for this discussion. Yes?
You talked about cost and price not being the same here. So you talked about like domestic tax incentives. Did you also look at foreign government policies and sort of seeing if the prices we're seeing are really not reflective of what costs are right now?
Right. So we have not done that. These are global numbers in terms of prices, panel prices. Yeah, but of course that is the input that you want to use in a levelized cost calculation for electricity, because that's what the investor has to pay the price of the panels. Now, okay, go ahead.
Well, sure, but what if those costs are unsustainable, right? I mean, what if you can't sustain that, everyone loses money, and the marginal cost is actually much higher?
That's right. And that, of course, is what we are observing at the moment. So this learning curve actually has, as of late, in the last couple of years, because of the cutthroat competition, these prices have become non-sustainable, and we have fallen even faster over the last couple of years than the 80% learning curve would suggest. So when we try to ask the question, what is economically sustainable, we did sort of an as-if calculation and said, if the industry had stayed on it the way it did in the past, which presumably was sustainable, where would prices then be? And that was the result that I slipped in there. Then basically your levelized cost numbers would be about 15% higher than what we're showing at the, or what we're observing at the moment. Yes.
So the gas and coal calculations don't include the externalities such as the health impacts, and so they're not really the full cost.
Right, right. And that's a very good point. Let me just come back here. This is just a wholesale price, and we're saying from all other perspectives, these two things are equivalent. So the externality or the social cost that I'm thinking about, of course, immediately is CO2 emissions. So ask yourself, you can play that model very easily. You can extend it and ask, where would, if you try to account for the social cost of emissions, by asking how high would the carbon tax have to be so that the price levelized cost of gas would catch up with that of solar. The answer at the moment is you would have to see something like $60 per ton. So if you were to slap that on as a carbon tax, then the two would really be competitive.
At this point?
At this point. Mm-hmm. Again, things get better in the learning curve scenario.
Could you please go back to your graph?
This one?
Yeah. So you make an assumption about balancing system costs going down 7% every year. What is it based on? Because it looks like those costs are kind of, this activity is like down to the earth. It's very basic, and there is not a lot of innovation going on there.
Yes, and on this one, of all the input parameters that we have, I feel we're sort of on softest ground there. So this is based on some industry reports. It's also a relatively short learning curve. These costs have come down, but I feel we have sort of the least, let's say, sound empirical basis to make that projection. So ultimately, we have a short history, and we went with some industry reports. Given what I showed you earlier about the importance of balance of systems costs, I think that needs a lot more work, because that's going to be ultimately perhaps the sticking point in all of this if panel prices keep coming down. I've been told that we're really out of time. Thank you for your attention.